Very good afternoon, good evening to all. Thank you very much for I would like to thank the organizers for giving me the opportunity to be part of this training program. And after listening to comprehensive presentations by the previous speakers, I would like to start again with some basics on air pollution dispersion modeling in urban areas and estimation of assimilative capacity. Next slide, please. In this presentation, I made it in the 4 blocks, like general aspects of air pollution, what is air pollution, and different types and scales of air pollution, sources and pollutants, and national ambient air quality standards, and then air pollution management, air quality monitoring, and air pollution modeling comprises the total air pollution management, and emphasis is given to air pollution modeling. And then estimation of assimilative capacity to define any airshed, how assimilative capacity can be utilized based on ventilation coefficient. One can define the airshed, and some case studies which were done previously by our group. And I would like to tell next 25 to 30 minutes on this. So the general definition of air pollution, as all we know, it is generally defined as an atmospheric condition in which substances are present at concentrations higher than their normal ambient, that is clean atmospheric levels, to produce significant impacts on humans, animals, vegetation, or materials. And in the table where the ambient clean atmospheric concentrations are given for different constituents of atmospheric gaseous envelope. On the left-hand side, we have the normal atmospheric gases, nitrogen, oxygen, argon, and some gases, including the water vapor. They are present normally in that. And on the right-hand side, we have the pollutant gases, carbon monoxide, methane, carbon monoxide, sulfur dioxide, ammonia, NOx, and ozone, which are present in the atmosphere naturally at a very lower concentrations. The trace amounts of pollutant gas are there in the atmosphere. And as we know, air pollution is not only an emissions problem, it is also a weather-related condition or phenomena. As such, it should be considered as a weather hazard. Like we have the smog and visibility reduction, climate change problems, ozone depletion, all that. And because of the emission of the air pollutant gases and particulate matter in the atmosphere in the foggy conditions in winter, the famous example of Delhi and North Indian cities, we have a lot of smog, because of which the visibility gets reduced, and several flights get cancelled, and trains get delayed or cancelled like that. As such, the air pollution also should be considered as a weather hazard. Next slide, please. And we would like to look at some of the types and scales of air pollution, wherein we have, depending on the horizontal extent of the horizontal dimensions and vertical, and on the temporal scale, what is the level of sources will be there in that area, like, and what are the associated sources will be there in those areas and types of air pollution. And broadly, they can be put into 3 categories, like indoor, local, and urban types of air pollution: regional, continental, and hemispheric. And in the indoor, wherein the indoor air pollution in houses and commercial complexes or offices are where human population will be there, which affects the people who live in that indoor regions. The horizontal scale will be up to 100 meters, and the vertical scale up to say 10 meters, maybe one building height, a couple of buildings or 2-floor heights, and up to the activity maybe up to 1 hour, which impacts the humans dwelling in that indoor, and like museums wherein the artifacts were displayed, they also get affected because of the intrusion of the outdoor ambient air intrusion into the museums. That is called the indoor pollution. And in the outdoor pollution, we have the local and urban. which are up to, in the local areas, up to 10 kilometers extent in the horizontal and 3 kilometers up to height in the vertical. And the activity can be up to 1 hour. Like the urban local bodies like municipality or any ward of that municipality area, wherein isolated factories or some power plants or waste disposal sites or vehicular movement will be there, all that will be taking place in that local scale. Similarly, in the urban areas, we go from 10 kilometers to up to 100 kilometers in the horizontal and up to 3 kilometers in the vertical. The pollutants can get transported. And the temporal scale from hours to few hours to up to 4 days, wherein a wide variety of urban sources, like as I said before, the any pharma industries or chemical factories there in that area, and the power plants in those areas, and the waste disposal sites, waste burning, domestic waste burning, solid waste transferring stations, landfill sites, all that, along with of course the major pollution from the vehicular sources. In any urban area or a city, we have lot many vehicles registered every day, and they have been plying on the roads, causing a lot of air pollution. And also the type of construction goes in the urban areas. The construction field also will add to the air pollution, along with crematoria and other sources. And in the regional scale, when you go up to thousands of kilometers, here in the urban, we have the mesoscale also, wherein when we come to the discussion, we'll discuss that. And in the regional, up to thousands of kilometers, and up to 15 kilometers in the vertical, like the beyond the tropospheric height, the activities can be there up to a temporal scale of 1 month, from few days to 1 month. Previous slide. And the types of organization will be the state or country, the interstate transportation of pollutants, like in the case of Delhi NCR, coming from adjacent states of Rajasthan, Punjab, like that. They are accounted for in this urban to regional scale. This is called the regional scale of air pollution, that is taken up by the transportation of pollutants, and ozone also in the vertical. What with respect to the ozone, what we see is the stratosphere, the ozone formation will be there, which protects the human beings from the ultraviolet B radiation, wherein the ozone will be treated as a pollutant in the troposphere. And in the continental scale of pollution, we have up to 10,000 of kilometers, up to 30 kilometers in the vertical, beyond the stratospheric, lower stratospheric heights, up to 1 year of activities. Country and world will get affected. Here in this case, in the vertical, in the regional and continental vertical scales, the chlorofluorocarbons and other things will get up to this, transported up to these heights, and there as being inert, they'll be dwelling there for longer duration of time, and depletes the ozone layer, which we know very well. And the airplanes, jet planes moving across the world, across the globe at those heights also contribute to air pollution. And hemispheric, beyond the 10,000 kilometers, up to 50 kilometers in the height, and up to 10 years in worldwide, where the climate change and greenhouse things are there. So by knowing these types and the scales of air pollution issues, the kind of dispersion modeling or the kind of transport modeling, chemical modeling can be applied, which we'll see in the next discussion. Next slide, please. So having known the definition of air pollution and the types and scales of the air pollution, the air pollutants are primarily divided into two categories, like primary air pollutants and the secondary air pollutants. The primary air pollutants emitted directly from the sources and not undergoing any chemical or physical transformation, they are called the primary pollutants. And secondary pollutants, from which the primary pollutants released from the sources, and when they enter the atmosphere, as a result of which there will be reactions among the pollutants and water vapor present in the atmosphere, and associated pollutants, gases. They'll get the generation of secondary air pollutants will be there, like say, salt particles, acid droplets, and sulfates and nitrates, because of which the acid deposition will be there. And of course, ozone is another famous example of secondary air pollution creation. And we have several sources, as we have seen in the urban areas. Industrial sources will be there, like power plants and the cement factories and all other small scale to medium scale industries and refineries, etc. They all emit particulate matter and SO2 and NOx into the atmosphere. And the agricultural rural sources are there, and the natural sources like volcanoes and all. And in the urban sector, we have the transportation, which is very highly polluting the atmosphere, the lower atmosphere, because of which a lot of health issues are also coming up. And knowing about these sources is important in the dispersion modeling. And what are all the main air pollutants in the atmosphere we encounter are the dust like particulate matter, the aerosols, and particulate associated with associated heavy metals like arsenic, lead, nickel, mercury, etc., and biological pollutants, and gaseous pollutants like sulfur dioxide, nitrogen dioxide, and interaction with among the pollutants, oxys, nitrogen also will be formed, carbon monoxide, carbon dioxide, which are already there. Hello, can you, and the volatile organic compounds and the odorous pollutants like mercaptans, ammonia, etc. also will be released from different types of industries. And we need to know about the what are the significant pollutants and what are the significant sources in any urban area or any area wherein we need to treat them for studying the dispersion of air pollutants. The next slide, please. We all know the regulatory laws and control is required for effective approaches to avoid the air pollution, wherein taxation, land use controls, and source specific emission standards and air quality standards need to be developed and reviewed periodically. There are laws in India since 1981, like Water Prevention and Control Act of Pollution in 1974, Air Prevention and Control Act in 1981, Environmental Protection Act in 1986, after the famous Bhopal gas tragedy. The EPA Act has come into the picture, and the AA notification has come into 2006 and is being reviewed now extensively. And in the National Ambient Air Quality Standards were prescribed in 2009, wherein 12 parameters are given. Earlier, we used to have only the classification will be there separately for commercial areas, residential areas, industrial areas like that. But all these grouped together in only one category from 2000 since 2009, and there are only two classifications: the industrial, mixed use, commercial, and residential areas are grouped into one, and another is ecologically sensitive areas, wherein all 12 parameters were given standards for based on 24-hour averages and 4 or 8 hour averages for carbon monoxide, 1 hour average for ozone, like that. And now BAP, the benzoyl alpha pyrene, is also included because it gives carcinogenic effects leading to the cancer. So several pollutants are included in the National Ambient Air Quality Standards. Next slide, please. And for any urban areas or cities to have the action plan, city action plans, or taking some regulations, the regulatory bodies have to be going through some air pollution management. The air pollution management as such will constitute the information on several things, like what are the types of air polluting sources, and what are the emissions, different emissions coming from that, and which are the pollutants are specific in those areas, and local meteorology and local topography is required. And the ambient air quality monitoring, which was extensively discussed by Tripathi sir, wherein all the 12 parameters, and depending on the city specific sources, the type of pollutants need to be monitored periodically, and the database will be helpful for regulatory authorities to make the further improve the national ambient air quality standards or emission standards, for which the air pollution model can be utilized. The air quality model is nothing but the dispersion model, air mass dispersion model, which takes the inputs of the types of sources, emissions, and various pollutants, and local meteorology, topography, associated thing like any in the city. For example, any coastal area is there, coastal waters also considered in the study area, and ambient air quality monitoring will give you the background air quality levels. The model predicts the pollutant levels, and with the monitored pollutant levels, the model predicted levels can be calibrated, and again the desired pollutant levels can be obtained by comparing with the national ambient air quality standards. If they're far exceeding in any urban city, if the ambient levels of the pollutants are far exceeding the standards, then there needs to be an action plan, a regulation, by using some control measures at the source, and by putting stringent emission standards for controlling the pollution from the sources. For example, the chlorine HCl emissions like from chemical plants, etc., can be given stringent standards. For example, the thermal power plants, the mercury emissions were given this time, and the PM10 emission standards also stringently reduced. So to take such kind of regulatory action, the atmospheric dispersion models or the air quality models will play an important role there, wherein the district level planning or the urban local body level planning will be made to reduce the pollution in those areas. Next slide, please. And air pollution monitoring, which was already described earlier in extensively, wherein all the 12 parameters need to be monitored by various methods, and as per the regulatory purposes, we use the RDA samplers and PM2.5 samplers, and associated gases will be analyzed using the like, for example, SO2 modified this method, the improved Western Gate method, and modified Jacob-Heckesser method for NOx, like that. We use several instrumentation, and as I said before, we used to have only lead in previous to 2009. Now arsenic and nickel are also introduced into the national ambient air quality standards along with the benzene and BAP. This monitoring is required to know the level of pollution in that urban area, and which can be given as background information to the dispersion model to estimate the pollution levels due to various sources in that urban area, and then compare with these levels and national ambient air quality standards. The action plans can be prepared. Next slide, please. So the dispersion modeling will be another part, wherein I would like to discuss about what is air quality modeling. It is used for the prediction of ambient levels of pollutants and their impacts on the surrounding air environment due to different sources. The different sources which we have seen previously, industrial sources and others, which is the dispersion model, nothing but a numerical technique or methodology based on physical principles of estimating pollutants concentrations as a function of time and function of emission distribution and the attendant meteorological and geographical features. Like, you need to give the information on the local meteorology for knowing the dispersion turbulence of the atmosphere, and then the emission rates of the pollutants and characteristics of different sources need to be given. And again, the dispersion modeling can be divided into two scales, like the short range modeling and the long range modeling. As when we discuss the types of scales, we have come across the urban and local sources, which comes under the micro scale here. The local sources like industries, vehicles, etc. in rural urban areas are treated with short range modeling. And long range modeling, the mesoscale up to 100 kilometers, the transport and dispersion of the pollutants up to 100 kilometers will be taken care. And regional scale, transport of pollutants up to 1,000, and intercontinental beyond the 1,000 kilometers. And in all these models, one can have chemistry into it, and we can know about the information on the secondary pollutants, air pollutants also. But whereas for all practical purposes, we'll be using the micro scale in the urban, local and urban scale, wherein several models are available, like IAC-ST3 Industrial Source Complex Short-Term Model, and ADMS, Atmospheric Dispersion Modeling System, AERMOD, US EPA model, regulatory model, and CalPUF, CMAC, Community Multi-Scale Air Quality Model, like that. All these three models can treat the different types of sources, like point sources, nothing but the stacks, and area sources, wherein landfill sites, municipal solid waste burning, domestic waste burning, mining related or dust excavations, construction activities, all those can be considered as area sources. And the line sources are the automobile sources playing on the roads. The emissions from the vehicles can be taken as line sources and volume sources. Different types of the models are available for use in the micro scale, that is for local sources, wherein so different types of sources like industries, vehicles, and other activities taking place. And next slide, please. All these models basically in the micro scale are a solution to advection diffusion equation, wherein the normal distribution is considered an equation for elevated point sources for continuous emission of sources. Can be written, analytic equation can be in the form of Gaussian Plume equation, wherein concentration is Q upon 2 by U sigma by sigma z exponential minus 5 square by 2 sigma square exponential term in the vertical also will be there. In the figure, if you see elevated source is nothing but a stack, plume coming out of which is moving along the x-axis direction, and the wind is taken along the x-axis direction, like that. And with some assumptions, the advection diffusion equation can be brought to the Gaussian Plume equation, wherein we need to have the information, the Q, the source emission rate, that is the pollutant released per unit time, the plume rise, the effective stack height will be the summation of the physical stack height and the plume rise, and standard deviations of the constant distribution in the crosswind and the vertical wind directions, which are available from the empirical regulations and tables from the literature, can be used, and we can get the concentration at any desired location in the horizontal and the vertical levels at any given point of time. Next slide. So basically, many models which we have seen in previously will be using that, using this equation. Basically, the dispersion modeling is primarily having modules like emission inventory, that is nothing but the information on the source, polluting source, like the height of the stack and its characteristics, along with the pollutant emission rate, let's say sulfur dioxide, how much it is getting emitted per unit time, and meteorological data, and monitored ambient air quality concentrations. All these will be given as input to the dispersion model, and the dispersion model will be calibrated using the monitored ambient concentrations. And like in the previous scenario, previous lecture paper, Padmanabhan Madam, she talked about the business as usual scenario and the projected scenarios, wherein we can have the information on the emission inventory, the hotspots of emissions in a city can be identified, and we can use those information in the graded form and across the city from the hotspots, how they are getting dispersed and how they are impacted in the entire city in the form of isolates. We can have it, information on that. As I said, the models require the information on the source, that is emissions at their location, and characteristics like point that is elevated stack, location of the stack, emission rate of the pollutant in grams per second, stack height, stack internal diameter, stack gas exit velocity and exit temperature. And along with it, we need to have the information on the meteorology data, hourly wind speed, wind direction, temperature, relative humidity, cloud cover, mixing height, solar radiation, etc. And albedo and ceiling height and the surface reference length to know the surface friction velocity U star and convective velocity scale W star mixing height. All these can be derived using some meteorological models as well, or using the empirical relations one can have it. And the concentrations can be obtained at a given receptor, like any discrete receptor, wherein we can estimate, or over the entire city when the graded emission inventory is there. Because of those emissions across the city, we can have several grids, and in each grid point we can have, and we know the distribution of the pollutant concentrations over there. And based on that, we can city action plan also can be improved or generated like that. And similarly, apart from the point sources, we have the area sources for which the location, emission rate in grams per second per unit area is required, release height from which height the emission pollutants are being emitted, and length and breadth of the area source, and orientation angle of the rectangular area or the area source with respect to the north is given. And similarly, the linear volume sources, the location of the source, its emission rate and release rate is required, wherein the vehicular sources are treated as a single point. The entire road on which the vehicles are plying will be treated as an individual points, or a small infinitesimal small point sources, and integrated along the road to get the concentrations. So the dispersion model can be utilized for getting the pollutant concentrations, to know the level of pollutants individually, and to calculate the air quality index of that city or urban area, and to reduce that, what are the action plans required to reduce the emissions at the source, or after coming into the atmosphere, once released into the atmosphere, how it can be curtailed, like using various smog towers like that to reduce it, can be considered to, so that the levels of pollutants can be brought down to the better air quality index levels. Next slide, please. And this is the estimated capacity is kind of calculation which gives information about defining or delineation of an airshed. If any city area wherein we have the information on the mixing height and the average wind speed of that area, the product of the mixing height and the average wind speed will give us the ventilation coefficient. So the estimated capacity of the atmosphere can be determined in terms of ventilation coefficient, which is a product of mixing height and the average wind speed. The US National Meteorological Center and Atmospheric Environmental Canada has classified that high pollution potential occurs when the afternoon ventilation coefficient is less than 6,000 meters per second, and mean wind speed does not exceed 4 meters per second during the morning hours. The mixing height is less than 500 meters, and mean wind speed does not exceed 4 meters per second. A criteria given by the Stackpole and Gross way back in 70s, which can be still utilized as for estimation of the estimated capacity of that region. Up to what level, up to what extent can be the pollution can be taken by those cities because of various different sources. So the same criteria of morning hours can be assumed during the night time also. And I would like to, having discussed about the dispersion modeling and the estimated capacity definition, I would like to share some details on the case studies wherein we have studied the dispersion of the air pollutants. Next slide, please. Next slide. By application of different models, one can know the dispersion of air pollution over a city and urban area. In this case, for example, we have taken the Visakhapatnam Bowl area as a study area, wherein we have taken the major industries of about 9 to 10 major industries, of which 67 stacks, existing stacks were considered. And the industrial sources, the stack details and emission rates from these stacks are used as input to the Gaussian Plume model, which was discussed earlier. And the vehicular count data taken, and we have calculated, estimated the emission rates of the pollutants from the vehicular data and road length data. And Gaussian 3 model is used for estimating the pollutant concentrations due to the line sources. And the data, as I said in the previous slides, the source details, the meteorology, the hourly wind speed, wind direction, temperature, relative humidity, cloud cover, etc., solar radiation, etc., are being given. And we have taken discrete receptors at desired locations, where the ambient air quality was monitored, so that we can compare with the observed data. And the model validation is done by comparing with observations, and some statistical errors are being computed. This study has been done for Visakhapatnam Bowl area long back. The next slide will give us the definition of the ventilation quotient, wherein the assimilative capacity of the Visakhapatnam Bowl area using the mixing height and wind speed data we have estimated. Next slide, please. We have estimated the ventilation quotient, and in 2 different seasons, summer and winter, wherein hourly mean wind speeds and the mixing heights were taken, and the product of which both will give the ventilation quotient in meters square per second. The ventilation quotient observations are like this: it's low during the early morning hours and during night, indicating high pollution potential occurs, because the stack pole criteria tells us less than 6,000 meters per meter square per second, and mean wind speed should not exceed 4 meters per second. The pollution potential will be high. Here, the pollution potential is observed during 11 to 17 hours, that is daytime. In both seasons, we have low pollution potential. That means it has higher assimilative capacity, wherein the pollutants can be safely released in those hours. However, in the early morning hours and in the late night hours, the high pollution potential will be high because of the lower assimilative capacity, or the values of the ventilation quotients are not meeting the safe criteria of the pollution potential. Yeah, then next slide, please. And here, as I said before, in the Visakhapatnam Bowl area, we have considered industrial sources for 9 to 10 major industries with 67 stacks. Data is given as industrial source, and the vehicular data at different traffic intersections were counted, and the emissions were calculated based on the emission factors of the pollutants and vehicle for different vehicles types and the road length. And using these two, we have used the Gaussian Plume model for industrial sources alone, and Gaussian 3 model for vehicle sources alone, and then we combine together to compare with the actual modeled values at those ambient levels of pollutants at one particular station. Here, just representation purpose, I have given it. If you look at it, the solid blue line gives the industrial sources alone data, estimated values, and the dashed line gives the Gaussian 3 model results. But when we combine both, so when we can consider both the sources, and they are very well in agreement with the observed values. And similarly, these concentrations were subject to some statistical analysis, normal mean scalar error, fractional bias, and of agreement like that. And we have found when all the sources considered using different models, or even nowadays AERMOD can treat all the type of vehicles like CALP of all type of sources you can have, and the pollutant concentrations can be estimated. Like this, the consideration of all these sources is required to get the exact representation of the pollutant levels in that particular area, in the urban areas or cities which we are considering. Next slide, please. And recently, again, a few years back, again, we revisited by giving more meteorological information in the study area. The same study area is considered, wherein we have used a WRF model, WRF, to predict the pollutant, say the meteorological parameters at different grid points. Almost 3 points of meteorological points have come, and we combined this with AERMOD, giving the emissions from all the 67 industrial stacks and the vehicular data of the NOx, and we calculated the pollutant concentrations with the combined WRF-AERMOD model. And we have seen, next slide please. We have seen the NOx values because NOx is a major pollutant from the vehicular sources. We have seen this. This is a same Visakhapatnam Bowl area study area we have considered, wherein 3 nested domains were considered, 1 degree by 1 degree 2. We have come down to up to 3 kilometers to 3 kilometers in the study area. We have 3 meteorological data points, and again we interpolated and used it for generating the meteorological data and emissions data used by the AERMOD. And then we, with the different schemes of turbulence, we have checked, but for just preliminary sake, I have given 2 such atmospheric boundary schemes, parameterization schemes used in the WRF. With that, how the winds are generated and how the combined model has given the distribution of the pollutant sources for the study area or the city. So having information on these, one can go back and compare with the monitored ambient air quality levels or air quality index, and again revisit the emission scenario. Like that, one can utilize the atmospheric dispersion models for predicting the pollutant concentrations at desired locations or the entire area of the city, the distribution of pollutants in the current scenario and the future scenario with increased polluting sources, or by implementing certain control scenarios at the sources, how the emissions are being behaved and how they are contributing to the city pollution. Like that, we can generate the various scenarios and the action plans can be prepared. This is all all I have to say about. And if any questions are there, I'll be happy to take up.